Okay, for this question it says, for what values of x does f obtain a relative minimum? What are the relative minima? Select the correct answer choice below, and if necessary, fill in the answer to complete your choice. So what we're looking for in this example is a relative minimum. A minimum, the word minimum, is describing the y. And so what we're looking for is a small y value, or the smallest y value. Now that's with a slight caveat because we have the word relative. And the word relative added to the minimum means that we want to be able to look in a localized area relative to nearby the point we're looking at. And it doesn't have to be the smallest y value on the whole picture, it just has to be the smallest y value in the nearby area. So for this example, this picture that we're looking at here, we can see right here is a dip in the graph. And if we zoomed in on that place, we could see that this point right here, which is labeled as -4, -5, would be the smallest, that point has the smallest y value in that nearby area. And so we're going to say that -5 is the minimum, and it occurs at the x value of -4. And that's the only dip in this graph, and so this is the only relative minimum. So there's only going to be one relative minimum. The minimum value is -5, and it occurs at x equals -4. In the next part of this question it says, for what values of x does f obtain a relative maximum? What are the relative maxima? And select the correct choices below. If necessary, fill in the answer boxes to complete your choices. So for finding a relative maximum, this word maximum is describing y. So we're looking for a highest y value. Just modify that just a little bit with the word relative. That means that we want to be able to zoom in on a particular area, and that would have the highest y value in that area. So looking at the picture that we have here, I can see two places on the graph that achieve a peak. And if we were to zoom in on those two areas, I can see that those points would obtain a maximum in that area, the highest y value in that area. So for this one here, we would have a maximum of 2. That's a max y value of 2 at x equals 5. And for this one here, we have a max y value of -8. Not -8. A max y value of 3 at x equals -8. So these would be our relative maximums for this particular graph. Now notice that we do have one being higher than the other. So this max of 3 is higher than this max of 2. But that word as a part of the vocabulary relative is what allows this graph to have more than one. So that word relative says you're going to zoom in and only look at that isolated area, and for that isolated area we do have a maximum of 2. So once again, we're not looking for the maximum on the whole graph, we're looking to see if there are any little localized maximums. So there are 2 for this one. So we would select this answer choice here, saying that there are two relative maximum. The leftmost, meaning we're talking about this one first, has a maximum value of 3, which occurs at -8. Then the rightmost, we're now talking about this one, has a maximum value of 2, which occurs at 5.
For this question, it says, for what values of x does the function obtain a relative minimum? Find the relative minimum value. For what value or values does the function obtain a relative maximum? Find the relative maximum value. So a relative minimum and relative maximum, those are going to be the highest and lowest values, but in a localized area, localized interval. So what we're really looking for is not the lowest y value on the whole picture or the highest y value on the whole picture. We're looking for little peaks and valleys in the graph. So that's what we mean by relative. If we narrow our focus, to only this part of the picture relative to that area, we do have a maximum. And if we narrow our focus to this part of the picture, we do have a minimum. So we're not looking for the highest overall or the lowest overall. We're looking for those little peaks and valleys, those localized minimums, localized maximums. So let me erase my markings. And this peak that we have right here will be the location of my relative maximum. And that ordered pair has an x value and a y value. The x part is the where part, which is what's being asked in this part right here. For what values of x does the function obtain a relative, well, this is maximum, obtain a relative maximum, and then find that relative maximum. So this part C is asking for the x, and the part D is asking for the y. So you're going to answer for part C, -7, and for part D, 7. So this is the maximum value, and this is the location, the x at which the maximum occurs. So then this little dip right here, this little valley, that's going to be our relative min. That's happening at the ordered pair -1, -2. So that x value is the where part, and the y value is the actual min part. So for part A, we're going to say at x equals -1, that's where the minimum occurs, and then the actual minimum, relative minimum, is -2.
So in this question, we want to determine whether the function is even, odd, or neither even nor odd. So on the right here, I have the definitions of an even function and an odd function. And we need to decide whether this graph of a function follows the definition of even or follows the definition of odd. Or we can say that it is neither even nor odd. So let's think about the definition of even first. And the definition of even is that when you have a function, that it needs to follow this pattern, this formula. And in this example, or excuse me, in this definition, it says f of x equals f of -x. And essentially, this is talking about symmetry, but using function notation. So with symmetry, we're saying that we have the x's being opposite, and that's what you see inside the parentheses here. You have this x and this x being opposite of each other. And yet, even though those x's are opposites, you can see that the y values are the same. And this is really the definition of being symmetric about the y-axis. So let me give you a picture representation of this. So what we're saying is if you have y-axis symmetry, the y-axis is the vertical axis, then if you have a graph and the graph is symmetric about the y-axis, for any point to the right of the y-axis, that would look like xy, you would have a mirror of that point over the y-axis. And if you have a mirror, those y-coordinates would be the same, and yet the x-coordinate would be opposite. So if you have a point on your graph that is xy, you're going to have the mirror of that point over the y-axis. The mirror of that point would have opposite x's, but the same y's. And that is the same thing that these symbols here are telling us. We have the x's being opposite, and yet the y's are equal to each other. So we would use this version of the definition if we were given the equation of the function. In this example, we're given the picture, and so we're going to think about mirror image over the y-axis. So we have our y-axis, which is this vertical line here, and we need to see a mirror on either side of that y-axis. So that means that any point on the left should have a mirror of that point on the right. And you can see with the examples I'm showing you right here that I have some points on the left that do not have a mirror on the right. So this graph does not have symmetry around the y-axis, and it is not an even function because it doesn't have that symmetry. So we can cross off even for this example. So then let's take a look at the definition of the odd function. So for the odd function, we have this definition. This definition here would be used if we have an equation. It says negative f of x is equal to f of negative x. And when you have an odd function, you're going to be symmetric about the origin. And so what that means is that if your x's are opposite, your y's will also be opposite. So graphically, what that's saying is that your opposite quadrants, opposite over the origin, will have a mirror image. So if you have a point in the upper right-hand quadrant that is xy, and you have origin symmetry, you're going to have a mirror over the origin, and you have the opposite x value and the opposite y value. You could also use the other two quadrants. If you have the second quadrant, a point here, you would have the mirror in the fourth quadrant, negative x, negative y. And that is what this definition is saying here as well. This is the definition that you're going to use if you're given the equation. And here I have the x's being opposite of each other. And because of this negative here, the y values are also opposite of each other. So let's go back to our example here. This is a graph, and we want to think about the symmetry with this graph over the origin. So here's the origin. Sorry, my whiteboard was misbehaving there. Let's try again. Okay, I finally got my pen working. So I think what I was saying is that here is the origin, and we want to determine if this graph has origin symmetry. So any point that we have in the upper left-hand quadrant should have a mirror in the lower right. So that's quadrant 2 with quadrant 4. And you can see that I have points that are matching up with each other. If I continue on with points over here, I am getting mirror images of that over the origin. If I continue with points over here, I'm getting mirror images over the origin here. So this graph seems to have origin symmetry. This one is a little bit less obvious to people looking at the picture. So let me give you a strategy so that you can really determine if this picture does have that mirror image over the origin. So here's a strategy that you can use. What you can do is do two reflections. Reflect once over the x-axis and reflect once over the y-axis. So let's take this picture and imagine reflecting it over the x-axis. So if I do that, this right here is about 2 below. So when I mirror it, I'm going to mirror it to 2 above. And then we have this piece that goes off to the right like this, which is going to go off to the right and up. And we have this piece that goes to the left and down. So this piece will go to the left and up when we mirror it. So that's one reflection going over the x-axis. Now let's try a second reflection. If we're going to reflect over the y-axis, then right now I'm about 1 unit to the right. I would mirror 1 unit to the left. So this point would move here. And this piece that's going off up into the left would mirror to go, I think I said that backwards. It's going up and to the right. It would mirror to up to the left. This goes up and to the left, and it would mirror to go up and to the right. So what we're seeing is a mirror image going over the origin. So if we combine those two reflections, one reflection over x and one reflection over y, we get the two pieces lining up with each other. So this is an example of an odd function because it has origin symmetry. Now earlier we talked about the y-axis symmetry, and if we think about a reflection over the y-axis, this reflection would go over the y-axis like this, and you see that these two sides are not matching up. This bottom half would reflect over like this, and you can see that it's not matching up with a mirror on the other side. So this graph does not have y-axis symmetry, and it is not even. So on this question, we want to determine if a function is even, odd, or neither. The function that we're working with is f of x equals x to the 13th plus x to the 5th. So before we can determine whether this function is even or odd, we really need to know what the definition of that means. So I've got on the side over here a definition of an even function. A function is even if for every x in the domain it fits this pattern, f of x equals f of negative x. Now what these symbols are actually telling us is that the graph of an even function will be symmetric about the y-axis. Now that's not really that helpful in this example because we're not given a graph, we're given the equation. So if we had a graph, we would use the symmetry about the y-axis to decide if the function is even. But we need to use this definition here, f of x is equal to f of negative x. For a function to be odd, we have this definition. A function f is odd if for every x in the domain, negative f of x is equal to f of negative x. And these symbols is a way of telling us that the graph of an odd function will be symmetric about the origin. So what we need to do is we need to figure out if this equation fits this pattern of even function, f of x equals f of negative x, or if it fits this pattern of an odd function, negative f of x equals f of negative x. So I have a process down here that we can go through in order to see which pattern fits. So this is the process. We're going to determine if a function is even or odd algebraically from the equation. So what you notice is that both definitions involve f of negative x. So we are going to calculate f of negative x. And once we calculate it, we're going to take a look to see if that calculation comes out to be the same as the original function, or if that calculation comes out to be the opposite of the original function. So if it comes out to be the same, that is fitting the definition of equals, fitting the definition of an even function. And if it comes out to be the opposite, see this negative here is the opposite, that's fitting the definition of odd. And if it doesn't fit either of those patterns, then we say neither even nor odd. So that's the process that we're going to go through. So we're going to start with our function, f of x equals x to the 13th plus x to the 5th, and we're going to calculate f of negative x. That's negative x to the 13th plus negative x to the 5th. And if you have an odd number of negatives, that means that you're going to have a negative number. So this is going to be negative x to the 13th. And once again, we have an odd number of negatives, and that is negative x to the 5th. So we've done this calculation, f of negative x, and we got negative x to the 13th minus x to the 5th. So if we compare this to the original function that we have right here, I think it's very clear to see that they are not the same. So is it the same as f of x? No. And so we know that it is not an even function. And then we want to see, is it the opposite of f of x? So if we take and we factor out that negative, the negative will be the opposite. We factor out that negative, you can see that this is the opposite of f of x. And so it does fit the pattern of the opposite of f of x, and so it is an odd function. So it does fit that pattern, and we can say that f of x equals x to the 13th plus x to the 5th is an odd function. Okay, so here we have, this is almost like a continuation of the last example. However, the graph is a little bit different. So we have the graph on the left, and we want to answer these questions about the y-intercept. For what values of x is f of x less than or equal to 0? For how many values of x is f of x equal to -3? And what is the value of f of -2? So let's start with the y-intercept. A y-intercept is where the graph crosses or touches the y-axis. So we have the y-axis here. And we do have an intersection point. This point right here crosses the y-axis, and that point is 0, -1. So we have a y-intercept of 0, -1. Just pay attention to the writing in the blank or next to the blank about whether you're going to type -1 or you're going to type the ordered pair 0, -1. On the next part, we want to know for what values of x is f of x less than or equal to 0. Remember that f of x is the same thing as y, so this is really saying y is less than or equal to 0. For what values of x is y less than or equal to 0? So I've got my y scale highlighted in green there, and I just want to remind you that all of the points that are above the x-axis will have y being greater than 0. All of the points below the x-axis have y being less than 0. We know that from the y scale. And then right on top of the x-axis, that's when y is equal to 0. So we want to know when y is less than 0. That's going to be below the x-axis, and also when y is equal to 0, that's going to be on the x-axis. So let's highlight the points that are below. So that's these points here. Those are all the points with y values that are less than 0. And then we have some points that are on the x-axis. That's these points here that we want to include. And I want to know what values of x. So I want to write down, using interval notation, x values. So I can use my ruler again and think about when each one of these group of points start and stop. So this starts here with an x of -12, and that group of points stops at an x of -23/2. We do want to pay attention to whether we're including the endpoints or not. The endpoint here has an open circle, so we would not include that, and that would use a parenthesis to not include it in the set. However, the other end is on the x-axis, and it is a filled-in circle, so we want to include it. I'm writing in the wrong spot. Sorry about that. -12 to -23/2. So then we want to look at our next line, next group. It starts at an x of -8, and will stop at an x of 1. Both of these points have a filled-in circle and are going to be included, so we'll use brackets. And then we have this point over here, which is on the x-axis, and it is a single point on its own. Interval notation requires a lower bound and an upper bound, so we're not going to use interval notation. We'll use our curly braces and just list that one point in the set. and we're going to union these sets together. So these are all of the x values on this graph that have a y being less than or equal to 0, or f of x less than or equal to 0. I'm going to erase my markings here and address the next part. The next part says, for how many values of x is f of x equal to negative 3? So remember that f of x is y. So let's read that question again with y. For how many values of x is y equal to negative 3? So let's identify all of the ordered pairs with y equal to negative 3. I'm going to draw a horizontal line at y equal to negative 3. This horizontal line shows me on the whole coordinate plane all of the ordered pairs that have a y coordinate of negative 3, and I want to find the ones that are on the graph. So starting over here on the left, I notice that this open circle crosses through that point with a y coordinate of negative 3, but we have to remember that the open circle is not included in the graph, so we're not going to include that one. Here we have a point that crosses the line y equals negative 3, but it's not labeled. And even though it's not labeled, it is part of the graph because it's on the line. So we are going to include that as one of our intersection points. And then we have this point here, which is labeled as negative 4, negative 3. So that's our second intersection point. So we have two values of x where y is equal to negative 3 on this graph. Our final point, our final part says, what is the value of f of negative 2? So that notation, f of negative 2, tells me that x is equal to negative 2. F of negative 2 is the y part. And so I'm looking for an ordered pair on this graph that has an x of negative 2. So I'm going to draw a vertical line at x equal negative 2. And that vertical line at x equal negative 2 shows me all of the ordered pairs on this graph, or on this coordinate plane, that have an x of negative 2. And this vertical line crosses the graph right here. That point is not labeled, but that point would be negative 2, negative 1. And so I know that f of negative 2 is equal to the y value of negative 1. Thank you for checking out my videos. Have a great day.